Hey kids, welcome to section 6.1, the start of the chapter on normal distributions. Today you're going to learn how to identify the properties of a normal distribution, how to identify distributions as symmetric or skewed, and how to find the area under the standard normal distribution given various z-values. So lots of vocab always in the first section of each chapter. So remember, random variables can be either discrete or continuous. We learned that in previous chapters. Recall that a discrete variable cannot assume all values between any two given values of the variables. Remember, if you're going to include decimals and fractions, you're going to be using continuous variables. So, on the other hand, a continuous variable can assume all values between any two given values of the variables. Examples of continuous variables are the height of adult men, body temperature of rats, and cholesterol level of adults. Versus discrete variables, those would be like the number of cups of coffee you order at the diner or the number of minutes you run on the treadmill. Those are values that can't have any decimals. Many continuous variables, such as the ones that we just talked about, have distributions that are bell-shaped, and these are called approximately normally distributed variables. Lots of adjectives. This distribution is also known as a bell curve or a Gaussian distribution curve. And it's named after the German mathematician Carl Friedrich Gauss, and he invented all sorts of stuff about electricity and energy and all sorts of stuff. But the bell curve is something that lots of statisticians use in their experiments when they report the results, when they collect their data, and your college professors will sometimes grade your assignments and tests and papers on a bell curve, where they give a few F's, a few A's, a little bit more B's and D's, and they give the most C's in the class. No variable fits a normal distribution perfectly, and that's because the theoretical the normal distribution like aims to be the be all end all. Everybody wants to be a normally distributed variable, so that's why it's a theoretical distribution, because that's what everyone strives to be. If a random variable has a probability distribution whose graph is continuous, bell-shaped, and symmetric, those are the three requirements, then it's called a normal distribution. The graph is called a normal distribution curve when we actually draw the picture. Now, there's an equation to calculate some of these values in a normal distribution. Notice it uses the letter E in math, which is 2.71. This is a really crazy equation. You don't need to memorize it. Um, this slide talks to you about how the shape and position of a normal distribution curve depends on two parameters, the mean and the standard deviation. The two pictures illustrate what happens if you have the same mean but different standard deviations versus different means, same standard deviations. So notice in the top picture that when two distributions have the same mean, let's pretend they're both anchored at mean equals 0. Notice that if the standard deviation is 1, we have this higher red curve. But if the standard deviation is 2, we have the lower blue curve. And that's because if your standard deviation is bigger, it'll stretch the graph out from side to side, therefore making it shorter. In the bottom picture, now we have the same standard deviation. Both have standard deviations of 2, but notice that the curve on the left, the blue curve, has a mean of 0, and the curve on the right has a mean of 2. Notice they're the exact same shape. We've just picked it up and moved it over to the other side. So having a different mean does not change the shape of the distribution. It's having a different standard deviation that will make one taller than the other. So here are the 8 properties of a normal distribution. Again, this is the ideal theoretical one that every graph strives to be. The first is that a normal distribution curve is bell-shaped. That's the picture that I was just drawing, and that's the picture that you're going to draw over and over and over again. The mean, the median, and the mode are equal and are all located at the center of the distribution. We're going to see a picture of this on the next slide. We're in 2 slides. Number 3, a normal distribution curve is unimodal, i.e. it has only one mode, so you're only going to see one hump in each of the graphs. Number 4, the curve is symmetric about the mean, which is equivalent to saying that its shape is the same on both sides of a vertical line passing through the center. So if I have a line passing through the center, then I have exact same right and left halves, 50% on the right, 50% on the left. Number 5, the curve is continuous. That is, there's no gaps or holes. For each value of x, there is a corresponding value of y. Notice that you don't pick your pencil up at all the whole time you draw the curve. It's continuous. Number 6, the curve never touches the x-axis. So theoretically, no matter how far in either direction the curve extends, it never meets the x-axis, but it gets increasingly close. So when you draw your curves, you're never going to connect on the tails. It's always going to be disconnected. Number 7, the total area under a normal distribution curve is equal to 1 or 100%. This may seem unusual since the curve never touches the x-axis, but if you want to really prove why that's true, then save it for college. But notice that everything underneath this graph has an area of 1. Number 8, the area under the part of the normal curve that lies within 1 standard deviation of the mean is approximately 0.68 or 68%. Within 2 standard deviations of the mean is about 0.95 or 95%. And 3 standard deviations within the mean are 0.997 or 99.7. Hopefully that looks very similar to the empirical rule. 68, 95, 99.7. All right, so those are your properties of normal distributions. Now, when the data values are evenly distributed about the mean, the distribution is said to be a symmetric distribution. So that means whatever is on the right side is a direct copy of whatever is on the left side. Notice in this picture that you've got your 3 percentages along the bottom, 68%, 95%, and 99.7%. Notice that we have the mean in the center, and here's 1 standard deviation for the 68%, 2 for the 95%, and 3 standard deviations for 99.7. It's okay that if you add 34.13 and 34.13, you get 68.26%. Again, that's why it says about down at the bottom, in case you're thinking about adding up those numbers. Now, when the majority of the data values fall to the right or the left of the mean, the distribution is said to be symmetric. Ooh, careful. Hold on, let's read that again. When the majority of the data values fall to the left or the right of the mean, the distribution is said to be skewed. So if you've got more on the left side of the center, then your distribution is skewed. So if we look at something like this, if you have most of the values on the right side, it could look something like this. It shouldn't touch, but it's kind of smushy there. When the majority of the data values fall to the right of the mean, the distribution is said to be a negatively or left skewed distribution. That means that the mean is to the left of the median, and the mean and the mean are to the left of the mode. Now, look at the pictures. These make way more sense. So I just described what a left skewed distribution or negatively skewed distribution is. Take a look at the picture. You got your median in the center. Your mean is going to be closer to the tail, and your mode is on the other side. When it's symmetric, everything is all in the center. Mean, median, and mode, all lined up in the center, evenly right and left. When the majority of the data values fall to the left of the mean, the distribution is said to be a positively or right skewed distribution. The mean falls to the right of the median, and both the mean and the median fall to the right of the mode. Here's a picture to go with a distribution of a positively skewed. Notice that the median is always the one in the center, the mean is always closer to the tail, and the mode is on the other side. The tail of the curve indicates the direction of the skewness. So if the tail is on the right side, it's positively skewed. If the tail is on the left side, it's negatively skewed. Those pictures are really helpful in kind of placing where everything is. Now, since each normally distributed variable has its own mean and standard deviation, the shape and location of these curves will vary. So in practical applications, you would have to have some kind of table for each variable. But that's going to be a different table for every situation. And so, what statisticians have done is they have normalized or standardized the distributions so that the standard distribution always has a mean of 0 and a standard deviation of 1. If we can somehow transform every single situation down to a mean of 0 and a standard deviation of 1, then we can essentially compare them and make some conclusions about their differences or similarities. Now, the values under the curve also indicate proportion of the area. And so earlier, we talked about how the area underneath the curve is equal to 1. Well, now that we know the area under the curve is equal to 1, I can now look and say what percentage of the area is between a certain point or to the right of a certain point. So essentially, area and probability are synonymous in normal distributions and any other distributions. So all normally distributed variables can be transformed into the standard normal distributed variable by using the formula for z-score. So value minus the mean divided by standard deviation. If it's written in terms of Greek letters, you've got z equals x minus mu over sigma. But if you're looking at regular z-scores, it's x minus x bar over s. And that's your standard z-score calculation. The z-value or the z-score is the number of standard deviations that a particular x value is away from the mean. So you can tell me how far something is from the mean and in which direction by telling me a z-score. For the solution of problems using the standard normal distribution, there's a two-step process. 1, draw a picture. 2, find the answer. Now, there are 3 different possibilities that come across in these different problems. You may be asked to find the value to the left, or to find the area to the left of a value. So maybe you've got 0 in the middle and the value on the right, and you want to find all the area shaded to the left. Or maybe your z is already on the left of 0 and you're still shading left. So shading left is one type of situation. Second type is if you're shading to the right. Now, if you're shading to the right and your z-score is on the left of 0, notice it covers more than 50%. If your z-score is on the right of 0 and you're shading to the right, notice that the area is going to be less than 50%. And then finally, if it's not shaded left and it's not shaded right, it could be shaded in between. So when you look at in-between values, you're looking to see how much of the area is in between a positive z-score and a negative z-score. Or maybe you just want the area between 2 positive z-scores, or maybe you want the area between 2 negative z-scores. Those are the 3 situations: to the left, to the right, and in between. Now, in order to calculate some of these different probabilities and areas, we need to use something called a z-score table. This z-score table that I gave you has one side that has positive z-scores and one side that has negative z-scores. So depending on what type of problem you're doing, you're going to use one side or the other to calculate all the probabilities. Now notice at the top that this graph is shaded to the left of a certain line. And then if we go to the other side, notice it's still shaded to the left of a certain line. That's super important because area underneath the curve or probability for a normal distribution is always area to the left of a curve. So let's see how we're going to actually do this. So find the area underneath the standard normal distribution curve. Draw a graph to support your answer. All right, so we're going to draw a graph. Same graph every time. We want to put 0 in the center. Then we want to figure out which side, right or left, z equals 2.09 is on. Well, positive z-scores are on the right, negative z-scores are on the left. So I'm going to just guess and say, okay, here's 2.09. Then after I guess where it is, I'm going to put a vertical line. And then I'm going to shade in the proper direction. In this case, it's left. Now I need to find the area under the curve. So I'm going to go to my z-score table. Since I want to the left of a certain z-score, all I have to do is find that z-score on the table and figure out what the number is. So I need a z-score of 2.09. So we're going to go to our z-score table. Let's maybe make this a little bit smaller. We need to find 2.09. So we're going to look down the left-hand side until we get to 2.0. And then we're going to look at the top. So let's get the pen real quick. So here's 2.0 and here's 0.09. Where they meet is my answer, 9817. So 0.9817. What does that mean? That means that about 98% of the curve I have shaded. 98% of the curve I have shaded. All right, let's take a look at letter B. Let's draw our curve. To the right of z equals negative 1.14. So find your 0. What side is negative 1.14 on? It's on the left-hand side because it's negative. So put it on the left. Draw a vertical line and shade to the right. Now, when I want to find the area this time, I need to do 1 minus whatever answer I get when I look up negative 1.14. That's because my z-score table is only going to give me what area is over here on the left. But my answer is all the area on the right. And so if everything underneath the curve is supposed to equal 1, and I want the right side, but my table only gives me the left side, I can subtract them. So I'm going to do 1 minus. Then I'm going to go to my z-score table, and I'm going to look up negative 1.14. All right, so negative 1.14. So we're going to find negative 1.14 is right here, 1271. Need my pen. 1271. Negative 1.14. So I'm going to do 1 minus 0.1271. And so I'm going to grab my calculator. 1 minus 0.1271 is 0.8729. Let's get that graphing calculator real quick. Hold on. All right. I've got my graphing calculator, so we're ready to go. Let's keep going. All right, letter C. Find the area between z equals 1.62 and z equals negative 1.35. So if I draw my graph and I put in 0, a z of 1.62 is going to be on the right. A z of negative 1.35 is on the left. Draw my 2 vertical lines. Now, if I want to find the area in between, what I'm going to do is I'm going to look up both of these z-scores on my probability z-score table. And then I'm going to subtract the bigger one minus the smaller one. So I'm going to look up 1.62 first. So if we look up 1.62, I need to go up to the positive side. 1.62 is going to be 0.9474. 0.9474. Then I'm going to subtract whatever my other z-score is, negative 1.35. So I'm going to go down to negative 1.35. Negative 1.35 is 0.0885. 0.0885. And then I can use my calculator to simplify and subtract, and I get area equals. So if I go over here and I say 0.9474 and I subtract 0.0885, I get 0.8589. All right, so that's how you find the area underneath a curve. 3 different situations. You're either graphing right, you're either graphing left, or you're graphing in between. Now, a normal distribution curve can be used as a probability distribution curve if it's normally distributed. So remember that a normal distribution is a continuous distribution, not a discrete probability distribution. And so as a result, this continuous curve means that there are no gaps. So that means every z value on the x-axis has a corresponding height. That means that the area underneath the distribution curve can be thought of as probability, or the proportion of the population that has a given characteristics. So this is where all the different word problems come in, because we can take a look at the mean and the standard deviation, and that allows us to see where a particular value can fall. For probabilities, a special notation is used to denote the probability of a standard normal variable. For example, if the problem is to find the probability of any z value between 0 and 2.32, then we're going to write it as the probability that 0 is less than z is less than 2.32. So basically saying that it's shaded in between 0 and 2.32. Now, because this is a continuous distribution, the probability of any exact value is going to be 0, because that value is represented by a vertical line, and you can't be on the vertical line if you're trying to be somewhere underneath the curve. So anytime you have any probabilities that are equal to something else, we just ignore them. And so the probability that A is less than or equal to Z is less than or equal to B just becomes the probability that A is less than Z is less than B. We don't have to worry about those vertical lines. They don't influence the total probability in any way. So now if we take a look at problems, the directions might say find the probability of each. Assume it's a standard normal distribution. So if I've got something written like A, the probability that Z is between 0 and 2.53, if I draw a picture, here's 0, here's 2.53, I'm looking for the area between them. So what's the probability that I'm in there? Well, notice that you're shading less than half, so I would assume that my value would be less than 0.5. Well, in order to do this, I'm shading in between, so I look up both values in my table, and then I subtract bigger minus smaller. So I'm going to first look up 2.53. So if I go to my z-score table, 2.53 is going to be, let's see if we can get it to show, 2.5012399943. And the z-score of 0 gives me a probability of 0.5. Number of 0 is right at the middle, and here's 0, and it says 0.5. So I'm going to subtract 0.5000, and when I do that, I get 0.4943. I did say that your value should be less than 0.5 because you're shading less than half a side. All right, if you've got something that looks like B, the probability that Z is less than 1.73. So I'm drawing a graph, and I've got 0 here, and I've got 1.73 over here. I'm drawing a vertical line, and I'm shading less than. So if I'm shading to the left, that means that I just get to look up on my table, and that's my answer. 1.73. 1.73 is going to be 0.9582. I expect that to be a pretty big number because not only am I shading half, but I'm shading almost up to a standard deviation of 2, which is where things start to get smaller and smaller in the tail. Okay, if I'm graphing letter C, the probability that Z is greater than 2.53, I've got 0 here in the center. I've got 2.53 on the right. I've got a vertical line, and I'm shading right. That means that when I look up the value on my table, I have to subtract from 1. So I look up my value on the table, 2.53. 2.53. That was 9943. So 1 minus 0.9943. My answer is 0.0057. I should expect it to be a very, very small number because 2.53 is getting into the outlier area, which means not much more is going to be going on. All right, now let's say we want to go the other way. So for instance, find the z-value such that the area under the standard normal distribution curve between 0 and the z-value is 0.2123. So if I draw a curve, I put 0 here, and it's between 0 and z. Well, they didn't say z and 0. They didn't say negative z. They said 0 and z. So z is going to be somewhere over here. Now it says that the area between, so that means I have a between. The area between is 2.2123, that area there. Well, if you go to the table and you try to find 2123, well, here's all the big numbers. 2, 1, 2, 3. Let's clear out this so it doesn't confuse us. 2, 1, 2, 3. Well, I got 2119. That looks like that might be the closest. So I'm thinking it's right there. Well, it's not exact. So what we're going to do is we're going to use the calculator to find the exact. To use the button, I'm going to go and I'm going to hit second and vars. Second and vars. Let's write that down. Second and vars. And then I'm going to use number 3, inverse norm. So that means I want to use the normal distribution, and I want to use it to find the inverse, or to go backwards. So I'm going to click on number 3. Now it says area, mean of 0, standard deviation of 1. Well, the area here is whatever area is to the left. Well, I know that there's a shaded part of 2123, but this unshaded part is 0.5. So technically, there's 0.7123 if we add it all up. So what we're going to do is we're going to try to find that z-score by using the function inverse norm, and we're going to plug in how much area is to the left of the z-score, which is 0.7123. So on my calculator, I'm going to type in 0.7123. I'm going to hit enter, and I drew my picture with a mean of 0, and the standard deviation is 1. That's a normal distribution. And I'm going to hit enter, and z-scores have 2 decimals. So I'm going to say 0.56. Now remember how I said we can kind of tell where it is? Take a look at that. 0.56. Oh, well, that's not what we said, is it? 2, 1, 2, 3. Oh, I was on the wrong side. My bad. The 2119, yeah, that's only for I forgot the 0.5. So I'm really looking for 7, what did we say? 7123. So let's try to look in here, but we got to go in the positives. 7123. 7123. Ooh, well, there, right there. It actually is on here. I totally didn't even notice. So that's 56. That's what we got. Perfect. Okay, find the z-value to the right of the mean, so that 54.78% of the area under the distribution curve lies to the left of it. All right, I need a graph. I need 0. I need the z-value to the right of the mean, so my z is over here. And 54.78% lies to the left of it. So this graph is shaded 54.78%. Well, to find the z-score that goes with it, we're going to do the opposite. Inverse norm. And how much area is to the left of this z-score? Well, everything to the left is shaded, unlike the problem above. And so all we have to do is plug in 0.5478. This is going to give me our z-score. So I can do second vars, inverse norm, 0.5478. Hit enter a few times. I should get a number bigger than 0.5 or bigger than 0, and I do. I get 0.12, which makes sense because we have more than 50% shaded, so I should have a z-value on the right of 0. Okay, if we take a look at the next one, I'm looking for a z-value so that 69.85% of the area is underneath the curve to the left of it. Well, again, I'm going to put a z-score on the right, and I'm going to shade. So that means that 69.85% is in that shaded region. That means that I can inverse norm 0.6985, and that's going to tell me my z-score. So second bars, inverse norm, 0.6985. That's going to give me a z-score of 0.52, which makes sense because that's bigger than 0, and I have a bigger than 50% graph. Okay, last one. If I have 88.10%, we put 0 here, we put z here. I expect this to be a fairly high z-score, maybe in the ones. So I want to inverse norm 0.8810. So inverse norm 0.8810. And I get 1.18. All right, kids, we will finish the rest of the notes in class. Keep calm and keep trucking.